Well, I know there's one of you out there. Hi, Abby. How are you? Discussion board won't let you post. I was seeing this issue from other students this morning too. I think it might be bug with Blackboard. But send me an email after we get done with the live stream and I'll take a look at it directly to see what's going on. But yeah, it should be letting you post. It was doing some funky stuff this week anyway, so that it may just be related to it. Because it also sent out announcements for me this week that I never actually published. So about the upcoming, I'm guessing, final. Okay, so what questions is Juliana asking you vicariously? No, I actually don't take off points for you submitting the discussion boards late. The discussion board due dates are more meant to kind of get you into a flow to understand like this is where you should be in the material. The only thing it's going to penalize you for if it's not done by Friday, that's when I do my attendance for the course. So you're going to show up as absent if you haven't completed it by Friday. But again, these due dates with the discussion boards are not meant to create a penalty. They're just there to say, okay, by this point, you should be able to answer these types of questions. By this point, you should be able to answer these types of questions. Do them when you can. This is an online course. It's meant to be a study at your own pace. If you're working a schedule where you've only got like Thursday afternoon to do everything Thursday afternoon. But again, the due dates are not punitive. They're merely there to create a framework on how to progress in the course. Oh dear. Okay, what does Juliana want to know? Question is, what is the significance of the acidity or alkalinity of redox reactions? Most reactions end with H+, so the solution becomes more acidic, but then in later videos you show how to make them basic. So there's actually two big questions that are actually I'm going to have to answer in order to answer that. So let's just look at a redox reaction. And hopefully I can invent one pretty quickly that is acidic or basic. Goes to CN solid plus SN plus 2AQ. And to balance this reaction, we've got 2H2O liquid and our 2H plus. So let's say we had this reaction. We have zinc oxide and zinc interconverting, so zinc gets reduced and tin gets oxidized. What's the importance of it being under acidic conditions? The reason we balance under acidic conditions, and just the balancing, is that it's easier. To go from acidic to basic conditions in terms of these types of reactions is pretty easy. In fact, I have a video on it, the course website. The short answer is convert all these to water. Put that many hydroxides on the other side, and then cancel out any common waters. And that will get you to the balanced reaction. The reason we care about acidic versus basic is more that, and this is something that kind of gets left out at this level, These are reversible reactions. So in terms of electrochemistry, we always look at reactions as if they're reversible. Even if practically they aren't, we still treat them as reversible reactions. Well, because they're reversible, we've still got Le Chatelier's principle. And so Le Chatelier's principle, by looking at H plus as a reactant here, if we run this under acidic conditions, this will drive the forward reaction. So this becomes more favorable for low pH. So pH is less than 7. If we were to run this under basic conditions, where we have a high concentration of hydroxide, this would become less favorable. Now, this is a particular reaction where the acid ends up having to be a reactant. If we run a battery that the acid ends up being a product, well, the acid is a product and we're under basic conditions, which means we have low H plus concentrations. This drives the forward reaction, making this a more favorable cell. So hopefully that kind of answers the question. We always balance under basic acidic because it's easy. Practically, we would run under basic conditions if, when we balance it, we end up with an H plus on the right. We'd run under acidic conditions if we end up with an H plus on the left. In terms of things to study for the final exam, there's actually 2 packets, and I need to release them because we're not doing seated courses. For the final exam, there is the new material, and then there is the review of the old material. So the review of the old material is just a shameless stapling together of all your old packets. But in terms of resources, best thing to do is just ask me, work old problems. I can assure you the final exam is not nearly as intense as my exams. To give you a feel, a lot of you took test 4. It's kind of that level of question, 1 to 2 concepts, but that said, it does spread over all the material. So we are going to go back to intermolecular forces and talk about what functional groups contribute to what intermolecular forces, which intermolecular forces are stronger, what their effects are on physical properties. The delta T equals KIM, all that's going to show back up. Now, in terms of what I give for the final, and I need to make sure I've got it up on the course website, is there's a formula sheet that I hand out at the end of every semester that gives you an idea of all the formulas that would be available to you. With the final exam, I typically give you everything with the exception of, I have to think about it. I don't think I give you like something trivial like converting centigrade to Kelvin, but I definitely give you most of the formulas that we've talked about this semester. The final is cumulative. 20% of the material is going to come from redox reactions and nuclear chemistry. Nuclear chemistry is super trivial. That should be the gimme ones. For the redox, they're very straightforward questions. So you're not balancing a full redox reaction, you're balancing a half redox reaction. You're calculating reference voltages, you're calculating cell potentials, and you're calculating how much mass is being plated. But there's not like unit conversions, and you're given a lot of the information to solve the problems. Is mostly your ability to put it together and get an answer. Now, before I forget, further on for Juliana, they all end with H plus in the reaction, but water has both. So we had the little subscript AQs up here. Water always has this going on. And we had that Blair diagram where we got H plus, goes back and forth to pH, goes back and forth to POH, goes back and forth to OH minus, goes back and forth to H plus. Just because we have H plus in the reaction doesn't mean that's the only thing that's going on. If we're in water, we have OH minus and H plus. The acidic versus basic condition just says what's the concentration of this. If it's basic, for your basic conditions, your concentration of H plus is less than the OH minus. Specifically, it's less than 10 to the negative 7 molar. If you're under acidic conditions, that's flipped. Under acidic conditions, the concentration of H plus is greater than OH minus, and the concentration is greater than 10 to the negative 7 molar. We don't go that in depth to electrochemistry, in Gen Chem 2. Two reasons. One, historically we just haven't. Two, this field is a bit more useful if you know calculus. Sounds weird to say, but there's a lot of electrochemical stuff that makes a lot more sense if you understand thermodynamics and you understand how to take derivatives. What other questions did she send for you or send you with? All right, so the discussion board this week was figuring out the oxidation states. So let me bring that up. So the reaction is H2O plus 3 manganese oxide plus hypochlorite, goes back and forth to 2H plus AQ plus 3 manganese plus 2 plus perchlorate, ClO4 minus 1 AQ. Ask you a series of questions. What's the oxidation state of manganese to begin with? What does it finish up as? What does chlorine start with? What does chlorine finish as? What species was oxidized? Which ones reduced? How many electrons were transferred? And possible pitfalls you'll get with doing this type of work. So let's start with oxidation states. So big pictures. We have ionic bonding and we have covalent bonding, and they represent opposite extremes. Covalent bonding assumes that the electrons are shared equally between two atoms. So when we look at, if we look at MnO2, we would say this is an ionic compound because it's manganese bound, it's a metal bound to a nonmetal. It's not that simple. Really, manganese in any type of bond, except for something like sodium bound to chloride, is going to sit somewhere between purely covalent and purely ionic. So covalent means the electrons are shared equally. So manganese and oxygen, basically a covalent bond would look like there's no electronegativity differences. The way we describe the charge under covalent conditions is what's called the formal charge. The ionic case is the other extreme. It assumes that electrons are 100% taken when atoms form in bonds. So manganese is giving up as many valence electrons as it can to oxygen, and oxygen is filling up its valence shells. To describe this, we use the oxidation state or number. The reality sits somewhere between the two of these, and I have to qualify that for you because there's whole fields of analytical chemistry that exist because this statement is true. The truth about manganese sits somewhere between the two of these. So if we look at something like manganese sulfide, sulfur is less electronegative than oxygen, so it's going to shift the charge closer to the formal charge, whereas MnO2 is going to shift it closer to the oxidation state. So that's just to start off. We're going to look at oxidation states, which assumes purely ionic bonding. There is 100% charge transfer between the atoms. Now, define the oxidation state the way I teach it and the way I think about it is you want to set up an algebraic formula. So we'll look at MnO2. Now, manganese and oxygen both have their own individual oxidation states, and at this level, we're going to treat them as if all the oxygens have the same oxidation state. This whole molecule has a charge, and the charge here is located on the upper right part of the molecule. If we don't see a number, the charge is 0. So if you look in the notes, excuse me, we've got rules and guidelines. Rules can never be broken, guidelines can be broken. One rule, one of the most important rules, is that if we add up the oxidation states of all the atoms in the molecule, we have to get the charge on the molecule. So the charge up here is 0, which is going to represent with the slash 0 through it, has to equal the oxidation state of manganese plus the oxidation state of the two oxygens. The second rule, which we always have to obey, is that the more electronegative element takes the negative charge. Oxygen's more electronegative than manganese, so it's going to take a negative oxidation state. That's all we can definitively say. So this is where our guidelines step in. And our guidelines are basically a way of guessing what is the most likely oxidation state. And it's actually kind of based on good rules. The easiest way to think about it is that everything wants to go back to the noble gas configuration. So if you go to the periodic table, what we get is that oxygen would prefer to lose 2 electrons to get to this -2 oxidation state. The halogens, fluorine, chlorine, bromine, iodine, acetine, all want to gain 1 electron to become noble gases. Column 1, they like to lose electrons. So lithium, sodium, potassium, rubidium, cesium, they like to lose that 1 electron to get to a +1. Calcium, beryllium, magnesium, calcium, strontium, barium, like to lose 2 to give you +2. I have a list on the course website about what the guidelines are. The big thing about the guidelines is that they can be broken. The rules will always trump them. So the counterexample I give is OF2. This actually puts oxygen in a positive oxidation state because fluorine is more electronegative. But again, the guidelines give us a good guess. Now, we don't have guidelines except for 4 of the transition metals. Yttrium and scandium are both +3. Zinc and cadmium are both +2. Some books will quote silver as being only +1. That isn't actually true. You can easily and stably isolate silver +2, so I teach that there is not a guideline for silver. Some books do, some professors do. Trust the electrochemist in my opinion. But anyway, we've got the charge on manganese plus twice the charge on oxygen here, which is -2 equals 0. So manganese here is in a +4 oxidation state. And this satisfies the criteria, or rule, the charge on manganese plus twice the charge on oxygen has to give us 0. So manganese is +4. If we look at hypochlorite, ClO, this -1 is the charge on the molecule. Now, a common mistake I see with this, and I'm saying this for people who are watching this video after the fact, this number does not tell you the oxidation state of the atom beside it. Oxygen is not in a -1. The -1 refers to the whole molecule, the sum of all the oxidation states. So chlorine plus oxygen's oxidation state equals -1, but that does not mean oxygen is in a -1 oxidation state. Again, our other rule, oxygen is more electronegative than chlorine, so it's going to take the negative charge. This gives chlorine a positive charge. Now, we have 2 guidelines here. Oxygen, sulfur prefer to be -2. Fluorine, chlorine, bromine, iodine prefer to be -1. We can't do the -1 for the chlorine because that would contradict our rule that chlorine has to have a positive charge. So we're going to have to go with our guideline that oxygen is -2. So this puts chlorine in a +1 oxidation state. Moving along, manganese is +2. Here for chlorite, chlorine is +7. So that's how we figure out the first few questions. Manganese here is in a +4, chlorine's in a +1. Manganese here is a +2. Where that +2 comes from, charge of the molecule is +2. We only have 1 element, so we know here that manganese is +2. And then for perchlorate, it's going to follow the same line of reasoning. We have 4 oxygen atoms, plus a chlorine has to give us that -1. Oxygen's more electronegative, which makes it negative, so we're going to guess -2. So here's your first 4 questions. Now, who's being oxidized and who's being reduced? And I saw this on the discussion board, and I'm glad that somebody pointed it out. There's an acronym, oil rig. And I really love this acronym because when I took high school chemistry, I actually failed the redox test. And I argued with the teacher teaching the course because I got every single question wrong, which is really hard to do. If you ever try to intentionally fail an exam, if you're just auditing the course, you're going to find it's really hard not to get any points. So I told him I clearly understood the concept, I just had oxidation and reduction flipped. He didn't give me the points back. But later on, somebody taught me oil rig. So oil rig, oxidation is losing electrons. Reduction is gaining electrons. Now, when we lose electrons, we get more positive. When we gain electrons, we get more negative. Negative. So, a few comments on this. I'll get to your comment in just a minute, Abby. So, a few comments on this. These are verbs. So oxidation and reduction are verbs. They do not care about where you're starting or where you're finishing. You're caring about the relative difference. Just because you're getting more positive does not mean you are positive. Just because you're getting more negative does not mean you're negative. You are reducing. The point here is that we see a shift towards more positive or towards more negative. So if an atom loses electrons, it is being oxidized regardless of its actual oxidation state. Reduction, if we are gaining electrons, if we are getting more negative, you're being reduced. Doesn't matter what the actual value of the states are. Manganese here is going from +4 to +2. It's getting more negative. So we would say that it is reduced. Chlorine has gone from +1 to +7. It's lost 6 electrons to make that happen. So we would call this oxidation. Now, the number of electrons gained or lost. Easiest way to figure it out for a reaction, figure out the element that's by itself. So we have one chlorine atom going from +1 to +7, so that's 6 electrons. The problem is this isn't always the case. We have 2 electrons here for manganese going from +4 to +2, but we have 3 manganese atoms. So again, we have 6 electrons. So when we talk about the electrons transferred, we mean total, not how many electrons are gained by each individual atom, but overall how many atoms are being gained by oxidation, lost by oxidation, and gained by reduction. So Abby said this is confusing. I wish we were in class. Yeah, this is actually a topic I tend to teach in Chem 1 for this very reason. At least hopefully when you get to Chem 2, it's a little bit more ingrained. Balancing redox reactions are hard, particularly the homework sets I post, unfortunately, are hard. They are much harder than anything you would ever see on the exam. That's also why I have the packets. The packets have a lot of worked examples as well. Balancing redox is hard because getting the number of electrons right is very hard. In this case, it helps that you've got chlorine, just one chlorine atom, but in the case that you have multiple atoms, like 3 manganese atoms here gaining 2 electrons, makes it a bit harder to see. The example I give, and if you've taken me for Chem 1, you've heard this example. If you and I both have $10 and ask how much money do we have, the answer is not $10. We have $20 total. Same thing's going to follow the electrons. Each manganese atom is gaining 2 electrons, but there's 3 of them doing it. So really that took 6 electrons, not 2. Now, that said, because balancing redox is considered more of a chemistry 1 concept, the examples here are going to be a bit easier. Not necessarily for the homework, but they are easier in terms of the final exam material. And yes, for the K even lab, even I got annoyed working with it because my goal was to work through it. I was like, oh, I'll do this really quickly. And yeah, when I didn't quite fill it to the right pipette line, it set me back to do it again. Now, honestly, it's something I wish we could do to you in lab and like constantly send you back, but there's only one of me and there's 16 of you, or 8 to 16 of you depending on the lab section. But yeah, I agree with you. The AI was super detail oriented. That said, I do kind of like that lab, or that version of that online lab, because a lot of people do try to cut corners in the lab. So yeah, I agree with you. I got frustrated doing it because the AI was so particular. But it's not necessarily bad to have that type of retentiveness given to you in terms of the homework. Now, I do wish we were doing the redox lab. I think the redox lab benefits you a lot more because you actually go through and you see how the Nernst equation works and you work with the Nernst equation. Balancing redox is okay, I guess. That was traditionally what was done with Chem 2 was a redox workshop. I'm the one that piloted the lab, designed the lab, so you would actually do an electrochemistry experiment. But yeah, there's only a few labs I really regret that you're not able to do. Le Chat's another one that's actually kind of fun. Actually, we had a pilot version due this semester that unfortunately was done by North Campus because they wanted on a slightly different schedule. They liked it. It's better than your old version, but y'all aren't going to get to enjoy like the new version of the Le Chatelier's lab. The K lab we do, it is what it is. I'm trying to come up with better ideas for that K lab. And I'm trying to think about what other labs you would have had this towards the end here. Calcium iodate lab's actually kind of cool. When you do the titration, it goes from like black to clear. But it's just a titration lab. I mean, it's interesting. It's nice and colorful. And actually, if you go to my videos, you can see like, I think I actually have a titration of calcium iodate to show when the transition period is. But that novelty kind of wears off when you do the titration 6 times. Now you are doing a solubility lab this week. I was seeing some issues with, actually I was only seeing one issue with getting the program running. Don't wait to do the solubility lab, particularly on the Wednesday section. The reason I'm saying that is, like I said, it is Wednesday. Don't wait to do that calcium iodate lab. It is a Java-based program. If you don't have the latest version of Java or you don't run Java on your browser, it's not going to let you launch it. So please go ahead and do it. Not so many people showed up today. There's a few more of you lurking in the background. So pre-labs and post-labs, don't worry about getting me pre-labs and post-labs before you do the lab. I'm still formulating what to do with your lab notebook. Odds are you're just going to take pictures of what you have in your lab notebook and send them to me. But the pre-labs and post-labs don't have to be completed before you do the lab right now because I'm not there to check them. We're just going to kind of do this in all in one fell swoop the week you do the lab practical. Now for the K lab, odds are, wow. Thanks for the autofocus there. In terms of the KA lab itself, I'm not going to require pre-lab or post-lab for that. The big reason is that it was kind of just a big online thing. So everything else, yeah, do a pre-lab and post-lab. For this K, don't worry about it. I'll just give you the 10 points on your lab notebook. Yes. If you for whatever reason have an issue with your internet connection while you're taking the test, email me immediately. It will show me on Blackboard when you were taking your test. So as long as you weren't sitting there taking the test for like an hour and like 10 minutes and you want the 5 minutes, because it does auto submit everything. But yeah, if you've been taking it for 10, 15, 20 minutes and suddenly cuts on you, shoot me an email. I can reset the assignment for you. It is a randomized pool, so keep that in mind that if I do reset the assignment for you, you're probably not going to get the questions. Same questions you were answering before, so you're just going to need to start over. There's only 1 or 2 questions per exam that are actually recycled. Most, I've created a pool of 4 questions to kind of cut down on the cheating, meaning they are similar questions, but they are not the same question. Yeah, and I'm thinking with the lab notebooks, because Ryan's asking about lab notebooks, I'm thinking with that, just take a picture and show me the grading marks and show me your pre-labs and post-labs. But I'll send more information about that as we get towards lab practical week. That week, it is an online practical. I will probably also open up an assignment saying, okay, take pictures of your pre-labs and post-labs since the pandemic, and also send me pictures of your pre-lab and post-labs before you left out with my signatures on it. And I'll tally those up to give you your lab notebook score. That's where I'm leaning towards right now. The big thing is just logistical. I don't know how big a document you can upload into Blackboard. Yeah, I'm getting the feeling that Spectrum has kind of historically not been doing a great job of maintaining the network, especially in the Raleigh area. I noticed that I constantly get kicked off first thing in the morning. So I think we're just kind of seeing the fact that there aren't any good cable choices in Raleigh and Wake County in general. So yeah, I totally sympathize. I've had a lot of mornings I've started responding to emails. Suddenly I'm getting an issue that I can't connect to the internet, and then later that afternoon I get an internet connection and suddenly realize all those emails I sent are saved to my browser. They were never sent, which is why students never got an answer back to their question. And it's incredibly annoying because you don't know at what point you got cut off. I personally don't think the router is the problem. I think Spectrum is the problem. So I actually have a pretty good Wi-Fi router. My cable box is okay. The cable router they gave me is okay, but I definitely, when trying to diagnose the issues with the lags in these videos, when I plugged this right into the router, I noticed that I really didn't get a big difference between going over the Wi-Fi versus the local area, just plugging directly in, which is not a good sign. Again, if you're having issues flipping note, this is the other reason you get the full week too. Like if you have internet connectivity issues, let me know. Like I can be very sympathetic towards that. It's different when it's like next Monday at 10 a.m. you say, oh, it kind of died on me. It's like, well, I mean, but you kind of wait at the last minute, right? Yeah, I really thought it was interesting when the cable companies blocked, because they were trying to pass a law that said that cable companies can no longer report the peak speeds. They have to repeat the average or report the average speeds in their advertising. They spent a lot of money to keep that from becoming a law. So the numbers they report are up to. You can get an internet connection up to this fast. The average values they won't report. And I actually had a roommate in grad school. He had a mainline connect. He did all his work. Um, he's actually was a theorist, so he would do all. It was computational, so he could do all this stuff remotely. And one night he actually got $20 off our cable bill because he texted them and said, like, I'm doing data packet streaming back and forth to the university, which is literally 3 miles away, and it's like on kilobytes per second. Like it's super slow. Like this is ridiculous. Y'all need just to refund us some of our money. And he won. I mean, he had like documentation showing that, yeah, that's literally 4 miles down the street. There is absolutely no reason for us to be down like kilobits per second. It's also why they gave us a little mascot when we got our cable, and that's why we'd always leave it with needles jammed in it whenever the cable repair guy came by. Yeah, I will hand it to Spectrum. They are relatively better than the internet service providers I had in California, but like relatively in that they're less bad. The other fun story we had was they would only do service calls when they had a critical mass of service calls to go do, so we canceled our cable, but they hadn't actually cut off our cable because they didn't have enough service calls in the area to justify coming out and shutting off our cable. So we watched the internet, we watched the Olympics and like everything, figure skating, like floor exercises, synchronized diving, everything, just to prove a point that we were going to watch our free cable until they cut it off. Because we had multiple arguments at that house because they used an indoor splitter for an outdoor application. So every 4 or 5 months it would rust out. We had to order it, and then we had to wait like a month for the service call to get there to actually get our splitter replaced. Is the glare any better on this board? I was working with videos this week and I replaced 2 of my lights with 2 other ones I had on hand. I think my diffusers were kind of lighting up. This was with a big white background. Yeah, I need to turn off the autofocus on this desktop camera, but yeah, good. Yeah, I was noticing a lot of my videos there's a big white blur here and a big white blur here for my diffuser. I mean, you can still see my lighting lamps in the background, but no, there is. So if you go to the course website under, there's actually final exam material. So there'll be lecture slides on how to balance redox reactions and how to do nuclear chemistry. So there's definitely slides on that. Now, I mean, you had me for Chem 1, so you're going to notice I recycled a lot of my slides from Chem 1. But that was mostly for the balancing redox stuff, and then the new stuff's also on there. The Word document, so the question is, for this lab this week, is there anything else that has to be submitted other than the Word document? That's it. Work the 4 titrations, submit evidence that you actually took it, what your score was, and that's all you're doing for the lab this week. For part B, making the lab. Not off the top of my head. My suggestion, so in terms of the simulation, you can do it as many times as you want. So if you're struggling with it and you get a low score, you can go back through and do it again. The point here is just get the exposure to the titrations and doing titrations of acids and bases, and I think there's a redox one for the 4th one, which was meant to... Oh wait, this week's the solubility lab, isn't it? Calcium iodate. Yeah, calcium iodate's this week. I'd have to look at the assignment. I don't know off the top of my head, so give me just a minute. So this is the assignment. The question is making the lab. I guess I'm a bit confused. Could you rephrase your question about what you mean by making the lab? For 6 salts in addition to table salt that we could observe the solubility. So there were 6 salts in addition to table salt that we could observe solubility. Do we need to sit there and record 3 different volumes for all 7 salts? No, I would not go through and do all 7 salts. Basically, you see from part 1 what the gist of the lab is. The question here is, can you back design an experiment? So pick 1 or 2 salts you think are most likely and focus on those. If you get what would be a good lab that meets what it's asking for, make a data table for each salts, demonstrate good experimental data, write the equilibrium expression for each salt, determine constant. Okay, you can just do that for 2 or 3. And I would say only do 3 if the first you do give pretty lousy data. But pick something with a low solubility. But that would be my recommendation. But no, you don't need to do all 7 salts. Like, that's just way too intense. I don't want to give you an exercise in busy work. So if we don't have one-to-one solubility, so an example of this is something like, this is not a cliche example. Do calcium hydroxide. So it's an equilibrium problem. It's going to require your three things: your equilibrium constant, KSP, your expression for Q, which is calcium hydroxide squared times concentration of calcium. And it's going to require your IC table. So we're going to ignore the solid. With any KSP problem, we're going to assume everything, we just chunk the salt in there. And so we didn't start with any in the solution. We get plus X for calcium, and we get plus 2X for the hydroxide because there's a 2 in front of the hydroxide. So our good volumes are X and 2X. If we plug that in, we get 2X squared times X, which will give us 4X cubed. And then if we're given the concentration of something, so let's say we're given the concentration of calcium, we know the concentration of calcium equals X, or if we're given the concentration of hydroxide, the concentration of hydroxide equals 2X, so we would just solve for X. So solve for X based on the concentrations, plug that in, and that would give you KSP. Yeah, no problem. Streams are always going to be up, so if you need to check out because you're getting bad connection, go for it. Always available by email or also on Teams. Yeah, when it comes to figuring out the KSP, always, again, it's an equilibrium problem. Always build your tables, always build everything. And then typically this row is going to go in here anyway, and then you can figure out what you know or don't know. So if you're given a concentration, you can solve for the extent of reaction. If you're given KSP, you can figure out the extent of reaction, go back to concentration. Yeah. So it's X times whatever the coefficient is in the reaction. So if this were a 3 for whatever reason, it would be 3X to the third power. And that is a very common mistake. I see that a lot on test 3. So I answer Ryan's question first. I have a question about getting the pH with Ka and molarity. With that, is the process similar to making an IC table and trying to solve for the H plus molarity? Yes. So this test 4 material is just a subset of the test 3 material. You're still going to build your IC tables. Give me just a minute. So we'll do something simple. Acetic acid, H3O2. There's a H plus plus C2H3O2. And you get KQ, it's H plus, C2H3O2 minus 1, all over HC2H3O2. And you got your IC table. So parent acid, H plus, conjugate acid. When you're being asked to solve for initial concentrations, it's usually these two squares that you're solving for, and you leave them as dummy variables. If you're being asked to find pH, we have the relationship that pH is the negative log of the concentration of H plus. So if you're being asked to find pH, odds are the rest of this table has been given to you. you're solving for the extended reaction probably through the quadratic equation. You're always going to end up with a positive root in this case because concentration of H plus is X. And then you just take the negative log of that number. Once you have a concentration of H plus, you can go to any of the values, pH, POH, and OH minus. Now, to answer Isaac's questions, have we gone over material other than the redox? No, today would have actually, if we'd had class, today would have been a review of Chem 1. We would have talked about how to balance a redox reaction, how to find oxidation states, and that probably would have taken up the whole class because most people have varying backgrounds. Some instructors basically barely teach redox. Some instructors like me go through the full balancing half reaction and balancing a full reaction. So today would have been catch up for everyone. And then next week we would have followed with deriving and proving the Nernst equation, working with the Nernst equation, and the plating equation. So based on how much current you've run, how much material did you gain or lose on the anode or cathode. And then usually we can cover nuclear in one day. It's not that hard. And then we would have followed up with review. But yeah, today would have just, and even with today is just more of a review for anything that you're kind of forgetting from Chem 1. Because finding oxidation states, you had to know that when you were naming compounds. So things, when you had to name the transition metals, you had to figure out their oxidation states for the name, and so you probably already had some background with naming them, finding oxidation states from names. It's just been a while since you've had to do it. Sure, you can ask any question you want. Okay, so yeah, you are free to ask any questions you want. So if you got questions on the on the packets for test 4, the test is still open until next Monday. So, and actually you can ask it at any time. Showing where you use polysolve, just write that on there that you used polysolve. The big thing is that you've gotten to a point that you've shown me a quadratic, and then if you use the quadratic formula, use polysolve, that's fine. But you need to show that you got to a point where you would have actually like had numbers to put into polysolve. So page 2, it talks about polyatomic ions to make buffers. So let me bring that up.
So I'll switch so you can see. They should ask about, my apologies, for that particle section. I'm so confused about which I should know which does which. So let me bring up the example so people can see it down the road. Where are you? OBX. Okay. So this is the couple of questions being asked. Which of the following compounds would be ideal for making a buffer with nitrous acid? TiNO2, NaNO2, cesium nitrate, NH4, NO2, AgNO3, and boron trinitrite. So this type of question, the reason I started asking this type of question was that students were proposing, there were two issues with their buffers. The first is that what they were proposing was not the conjugate base. The second is that what they were proposing wasn't even soluble in water. So if we have HNO2 as our apparent acid, well, a buffer is a combination of a weak acid and its conjugate base, or a weak base and its conjugate acid. So whatever we combine to make a buffer with HNO3 has to contain nitrite. So if we look at that list, there are several compounds there that contain nitrate. So that silver 1 nitrate, AgNO3 on the top right, won't work. The cesium nitrate, CsNO3, will not work. And that's the only ones. Now, the other thing, and this was more to address an issue I was seeing with students when they answer these types of questions, it has to be soluble. So if you put something there like titanium nitrite, the issue with titanium nitrite is there's not a solubility rule associated with either the Ti or the NO2, and so you can put TiNO2 in there, it's going to be a solid and it's not going to react. So not only does it have to contain the conjugate, it has to be soluble in water. And this again was addressing more issues I was seeing with students coming back and saying, well, you can put any nitrite in there. Well, that's not true. So if we look at the options here, we've got sodium nitrite, NaO2, which would be a good choice. We have a solubility rule associated with sodium. Boron nitrite, BnO2 taken 3 times, would be a poor choice because we don't have a solubility rule associated with boron. The ammonium nitrate is not a bad choice per se. That is soluble. That said, that's also an acidic salt. So your answer here is the sodium nitrite in terms of making a buffer. This is far beyond, this was more meant to address issues I saw with students and how they were rationalizing how to pick it. But that's more what it's getting at, is like, do you recognize that it has to contain nitrite and then it has to be soluble in water? HCl3 is not defined as a strong acid. It is one of those borderline acids, but it is definitely not a strong acid. So HClO4 perchloric acid, that is definitely a strong acid. But HClO3, there is some of the HClO3 that remains in solution after dissociation. It's a strong weak acid, but it is still just a weak acid. Now, chlorate, ClO3, does, I think that's the ones that follows our solubility rules. So if you have ClO3 with something, it typically dissociates entirely, or it's very soluble in water. With HClO3, the reason why it's not a strong acid is that there is still some electron density left between the oxygen and the hydrogen. So this goes back to oxo acids. The more oxygens you add, the better the acid becomes. ClO4 has more oxygens than ClO3, so ClO4 is actually going to be the better acid.
Yeah, the big thing is find the conjugate base. That ion has to be in the whatever you're adding. And the additional thing is that it has to be soluble in water. Because you can have all the nitrite in the world, but if it doesn't dissolve in water, you're not making a buffer solution. I think it was just more to kind of put you there. There aren't those types of questions on the exam. That was more meant for an in-class discussion to make sure students were thinking about how do you practically make a buffer. So Ryan's asked on the WebAssign quizzes, there was the section that asked us to fill in whether the salt would be acidic, basic, neutral, or it depends. Would it be conditions? What would be the conditions that would result in it depends? So we have an anion and a cation associated with our salt. So let's say we have A and C. We have our anion and cation. And to determine if it's an acidic or basic salt, the question we need to ask is, do the anions and cations react with water? So with the cation, generally it's going to absorb a hydroxide from water to give us COH plus H plus, and our anion is going to absorb hydrogen to give us HA and OH minus. Now, if neither of them, so we have to look on this side. This reaction does not occur if this is a strong base or this is a strong acid. So if they both, if we looked at something like sodium chloride, we'd have sodium hydroxide and HCl. Those are both strong acids, so neither of these reacts with water, so this would be neutral. If one reacts, let's say the cation interacts, so something like boron nitrate, BOH. Okay, BOH plus 2 is not a strong base, so this would react, but the nitrite here, NO3 would form HNO3, which is a strong acid, so it doesn't react. If we had the anion interact, so something like Na2CO3 to form bicarbonate, that would react, so that would be basic. If we have a situation where both of them react, so let's say we had B2CO3 taken 3 times. If both the anion and the cation react with water to form a weak acid and a weak base, that would be an it depends scenario. Because one of them's acting like an acid, one's acting like a base. Well, acids and bases neutralize each other, but they're not equally strong acids and bases. So we would have to actually look up in tables of Kas and Kbs to figure out which one would have the more dominating effect on the reaction. So it's kind of the case where both of them react to form a weak acid and a weak base. So what's your question about titration curves? You're welcome, Ryan. So before titration, NO3 nitrate does not actually react with water. So NO3 itself is a neutral ion. If it were NO2, then if we had NO2 in solution, that would act as a base. It would go from NO2 to HNO2, and that would raise up the pH of the solution.
qualitative parts of titration curves. So I know what you're talking about. Down. You don't feel any calculated amount of acid in solution. There's steps to do it. All right, so he's asked a question about how do we figure out the concentration of the acid based on the titration curve. And let me bring one example up. So I'll flip it around so you can see it. But this is the first one in the packets. So we have a volume of 20 mLs at the equivalence point. We had that the pH is 8.76. And we have the pH at the midpoint here is 4.74. The additional information that we're given, which is beneath the problem, is the molarity of the base is 0.150 molar. The volume of the acid is 30 ml. And you're asked for all that other information. So let's focus first on just finding the concentration of the acid because that's what he's asked. And let's talk about the other things you can get out of this as well. So to figure out the concentration of the acid, we have what's called the master neutralization formula. It says the molarity of the acid times the volume of the acid over the reaction coefficient of the acid equals the molarity of the base times the volume of the base all over the reaction coefficient of the base. So this statement is always true. Now, the problem specifies, and it specifies a very, very good reason, this is a monoprotic acid with a monobasic base. So we have HA plus BOH going to AB plus H2O. So we have our acid, our base, the salt that's created, and the water. And the reason we put the stipulation of a monoprotic acid and a monobasic base is it means that they are 1-to-1. If it was a diprotic acid or a dibasic base, it would create a 1-to-2 ratio. So we need these coefficients to stick into this equation. So this number we go here, this number we go here. Now, when we do this mono to mono, it ends up simplifying the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So it greatly simplifies the equation, but you can do this for a diprotic, triprotic, whatever. You're given the molarity of the base, the problem statement, 0.150, and you're given the volume of the acid in the problem statement. The VB, the volume of the base, is just our volume at the equivalence point. So this 20 ml. Now, we can get away working with milliliters, not liters, because volume is on both sides. So let's see here. Get what? Molarity of acid, I think here is 0.100 molar. So to figure out the concentration of the acid, it's just the neutralization formula for your volume at equivalence and the two other pieces of information you had to be given to solve this problem. Yeah, you're welcome. You're going to find this is probably the easiest test
other than the first exam that you take this semester. Ideally, I would lump this together with a previous exam, but that would make a very long exam. It would also put the exam after the withdrawal date. So I kind of use this as our curve for Chem 2. I hate to say that. Typically, people do very well in Test 4, and then the final is really the hardest exam you're going to take this semester. Not because it's like calculation intensive, it's just so many topics get covered. You have covered quite a bit of topics this semester. So that's kind of what makes the final hard, is that it's not focused. It's a lot of different material. So this is kind of given there to kind of like help your grades going into the final. But I still need to test on it, and there's several questions on the final that do concern pH and titration curves and things like that. I want to let you know before you get like past the withdrawal day that is not going to work out for you this semester. So yeah, we'll make that third test kind of hard, and then the fourth test focuses it. How would you get the PK and the KA? So the point here is the midpoint, and we have the Henderson-Hasselbalch relationship that says that at the midpoint, the pH equals the pKa. So off of one of these curves, this second pH, this 4.74, equals the pKa. This 8.76 is just distractor information. If students don't know what they're doing, they're going to try to do something with the 8.6 because it's given to them. Actually, you can backtrack out the pKb on that, but not worth it. So if you have the pKa from that, your Ka is just 10 to the minus pKa. Right? Glad I could help you today, Isaac. Yeah, these are pretty straightforward problems. Like once you work a few of them, you're like, oh, not that bad. I thought about adding diprotic and triprotic titrations in there just to add some degree of difficulty to reading these types of tables, but it's really kind of outside the scope of this class. And that's honestly how I want to modify the Ka lab. What we would have done would have been my version of the Ka lab. What I'd like to try in future semesters is actually getting you to do a titration of a diprotic and triprotic just to see the curves. They are actually pretty cool when you see the titrations because you see this pattern repeated for the number of protons in the molecule. But not going to happen this semester. Yeah, you and me both. I really wish we weren't doing this online. It looks like fall's looking very likely to be online as well. Summer is definitely online. I've had to start prepping for the summer courses as well. To make summer extra worse, we don't actually get the break we normally get in there. So semester was extended a week, which means we basically lost that break. All right. Thanks to you for showing up, Isaac. Yeah, I'll see you Monday when you come in for the next live stream. If there are any other questions, I will sign off. I will see you all next Monday. Please do take a look. The discussion board should be opened up for Monday. It's the Nernst equation. Nernst equation, play with it a few times, and we'll talk about next week where the Nernst equation comes from. It's actually something you've already worked with before. We just changed the units. That's it. So, see you all. Thank you all for showing up.